Good morning, everybody. Welcome to our weekly machine learning seminar. Today, we'll have a pleasure to have a talk from Orhan Ermis, who is a researcher in the Luxembourg Institute of Science and Technology in the Trust Group. And the topic of the presentation is already visible on the screen. So Orhan, you can say a few words about you and the virtual floor is yours. Go ahead, please.
Thank you, Jakub. This nice introduction, and thanks for this opportunity again. My name is Orhan Ermis. I'm a researcher at Trust Group, as Jakub said. My recent research domain is mainly detecting anomalies in computer networks or in telecom networks. Additionally, I am also working on privacy-preserving machine learning as well, and also I am working on watermarking with machine learning models. So yeah, in short, I can say that I'm using machine learning for security, and for some point of view, I am also using some cryptographic techniques or some other techniques to protect the machine learning models. So in this presentation, I will give you the talk about one part of our research work with Post Telecom, with Post Luxembourg. As you know, this is the Post is the one of the main telecom operators in Luxembourg. So we are working with them in the scope of RDI law projects. So, and as I said, this is some part of this research. As you can see that it's based on machine learning models and detecting attacks in specific networks, which are called SS7 networks. So this is the outline of my presentation. First of all, I will give some brief introduction about signaling systems, No7, which is SS7. And then I will talk about post solution. Then I will give our solution on this domain. So in order to detect attacks in SS7 networks, then I will talk about the experiments, conclusion, and the future works. So if I can briefly introduce the protocol to you, so we need signaling protocols in telecom networks. So their main job is to make the basic functions run in the network, like this is tier up or down the phone calls, SMS exchanges, or by using data internet with our phones. Now they are also responsible for the data transfer part as well. So the SS7 is an old protocol. This is mainly designed for PSTN, which is normal telephone networks, but then adapted by 2G technologies, later in 3G technologies. As you can see from the security, yeah, as you can look at it from the security perspective to the topic, since they are designed for legacy systems, there are many vulnerabilities in those networks. So attackers try to find those vulnerabilities and deployed several attacks on SS7 networks. Then the protocol is evolved. IETF, which is mainly responsible for telecom operations, you know, the standards, etc. So they introduced another protocol called signaling transport protocol. The idea is to use some wrapping in order to make available the TCP/IP protocols for the telecom communication, particularly for the core network. So this is the example illustration of 2G, 3G, SS7 networks. As you can see, there are many nodes, many entities in the network, but we are not going into every details for this. Basically, all you need to know for this presentation is the home location register, which is the database, main database for the subscribers. And the other one is SMS center. As you can understand from its name, it is related to organize the SMS exchanges in the network. And the third one is the MSC. The fourth one is the VLR. MSC is mainly responsible for the data and voice transfer between the subscriber and the core network. VLR is the temporary database while you visit another network. So usually you can consider the visiting network as the Belgium's telecom operators like Proximus network, and you can consider the home network as post telecom network. If you are in Luxembourg, you are in the, and you, if you are the subscriber of post, then you are in the home network. So if you go to Belgium with post subscription, then you will be in the visiting network mainly. So I will continue my presentation with the vulnerabilities of SS7. As you can see, there's a figure with respect to this, but it is I will give you more details about this figure by following the report of positive technologies on SS7 vulnerabilities. They categorize message exchanges into 3 groups for the SS7 core networks. The first one is the messages that are transmitted inside the network, home network. The second one is from home network to the visiting network. And the third one is from visiting network to the home network. So as you can see in the upper left-hand side, there's a figure, as I said in the beginning. So it shows the effect of using filtering mechanism against attacks that targets those categories. So, for instance, for the first one, if there is no filtering mechanisms, only 23% of attacks became successful. And if you use filtering mechanisms, you are able to eliminate all of them. For the category 2 attacks, 84% of the attacks are successful. But if you use some filtering mechanism, you can reduce this amount to the half. But if you have a look at the last point, the category 3 attacks, the category 3 messages, if attackers target those messages, then filtering mechanisms has some little effect when compared to other attacks that target category 1 and 2 in SS7 networks. So the main reason is that for the first 2 categories, the initiator is in the initiating node is in the home network. So it's your network. As a telecom operator, you can detect what is going on there, and you can easily find out the malicious nodes there. For the category 3 messages, you need some frequent data flow to your network. Therefore, you will have the knowledge of detecting whether the attack is malicious, whether the message initiator is malicious or not. So particularly for the roaming case, which we call it roaming, you are in the visiting network and you are trying to reach to your home network. For instance, you are in Belgium and you are calling your mother in Luxembourg, and then this is called as roaming in telecom, basically in telecom operations. So therefore, our idea is to use the historical data, mobility data of users, subscribers, and adapt machine learning models in order to detect attacks in SS7 networks. So our case study for this work is SMS interception attack. In the left-hand side, you can see the normal message exchanges, normal signaling message exchanges in the core network for SMS messages. So there are some procedures needs to be executed in the beginning in order to send the messages. like the sending authentication info or inserting subscriber data to the VLR, because we are assuming that yeah, the subscriber can be stable, or he or she can be mobile in the visiting network. So we need to update the location, etc. As you can see in the right-hand side of the figure, attacker is pretending like he is the MSC, and he is trying to send an update location request. And yeah, for this part we are avoiding the other message exchanges in the normal case, so we are just taking care of considering the most important ones in the SS7 protocol. So what we are doing is that attacker registers itself as a legitimate entity, as a new MSC in the system. So it gets the necessary information, then the operation is done, all the messages that needs to be sent to the subscriber will be sent to the attacker. This is pretty easy because, as I said in the beginning, SS7 is mainly designed for PSTN, which means it doesn't consider, by definition, it doesn't consider integrity or authentication like security merits. So this is why all the nodes entities in the network are vulnerable. Additionally, as you can see from this figure, although people started, companies and countries started to deploy 5G networks, and people start using 4G for many years, 2G, 3G networks are still in place. So there are some possibilities that may cause, even if you are using 5G networks, like they can initiate downgrade attacks, and they force the system to use legacy systems, then the attackers benefit from the vulnerabilities of those systems. Mainly SS7 protocol is the core part of roaming case, even if two operators are using, although they are using a 5G network, it is independent from this. So for the roaming case, telecom companies are still using SS7. And another thing is that although we are using 4G network, there are some studies that shows that the LTE networks, the 4G networks, have still have the same vulnerabilities like SS7 networks, and attackers can initiate the same attacks by using different entities in the network to 4G core network systems. So our contribution is that we are proposing a CNN-based approach, which is adapted from one of the studies in the literature, and we are also using the post solution for detecting those attacks in our study, but we are using the feature selection and mainly feature engineering part from there. So we have improved this solution in order to provide better detection rate. So and we conducted our experiments on both real world data and simulated data sets. So now I will talk about autoencoder-based solution, which is the solution proposed by Post, and this is the part of the Huang Chang's MS thesis. The tool is currently deployed to Post network, although they improved some features, etc. afterwards. They are mainly using the same tool. So they are analyzing the SS7 networks, and they are trying to adapt autoencoder-based scheme to detect attacks. So in order to make this analysis, they recorded the Post Luxembourg recorded 2 days of communications in including national and international traffic for more than 500 roaming partners. So therefore, they have almost 11.1 million unlabeled data, which means that we don't know whether the data is attack data or not. And we have 62 labeled records. Also, they are using another data set called one-time data set. And this is just consists of 100 records collected from, again, post network as well. So if you remember what I said in the beginning, in this study, our main is to use more sophisticated approach like machine learning, but also we need to use some mobility history of subscribers, because as a raw data, it is not possible to directly use it in machine learning applications. Therefore, we need to extract some meaningful information from there. So what they did is that by considering the geographical positioning of Luxembourg, which is close to 3 countries, and it is relatively smaller than the neighboring countries in the neighborhood, and therefore they put some extra properties, put some extra features in order to easily detect attacks, and based on the mobility history of users, they obtained the features that are shown in the left-hand side. I will not go into details for this table because there are 43 new features which are introduced for this study. They are like number of countries visited in a given time period, or velocity of the subscriber, etc. So for the autoencoder networks part, for those who doesn't know the details, autoencoder networks looks like this. And in the first part, in the encoder part, you extract meaningful information and discriminate the characteristics of the data set, and then you try to reconstruct the input data in the decoder part. So how they are using their solution? They are training. They are training the model by using the original, by using the unlabeled data, and then they are using the labeled part in order to fine tune the data, like optimizing the hyperparameters of the network. So based on the reconstruction error that they obtained from the input and the output of autoencoder, they are assigning a threshold to detect attacks, and then they are trying to figure out whether the input record is attack record or not. So according to their results, they obtained 69% accuracy and 69% average precision. So according to their results on one-time data set, so those first 2 of them are also belong to the one-time data set. There are 31 false positive events in the network, but the thing is that the normal traffic identified as an attack due to the short duration between 2 consecutive update location events, which are needed for the SMS exchanges. So therefore, we need a different solution that can learn attack patterns and normal events together with their exceptional situations. Therefore, we decided to work on a CNN-based solution, semi-supervised solution. So the first thing that we did in our study is to analyze the features. Actually, our main idea is not to use semi-supervised learning in the beginning. We were planning to use unsupervised learning. So we first analyzed the feature set. As I said in previous slides, there were 43 features, but we saw that some of them are not changing for attack or normal traffic records. Therefore, we conducted some experiments on this, and we tried to figure out whether the effects of the inputs to the outputs, or we tried to analyze the data set, and we employed mutual information and mean absolute difference for our analysis. And this was actually after we saw that unsupervised learning is not successful. So, and we decided to go further for the semi-supervised learning. Therefore, we take one approach from supervised learning and another approach from unsupervised learning, and we combine those results to obtain the new feature set. So now we have 31 features, and the idea is to use semi-supervised learning because we have an unbalanced data set. We have number of unlabeled records, which are correspond to 11.1 million approximately, and we have 62 labeled records. So it's not sufficient for supervised learning. As I said in the previous slide, unsupervised approaches are not efficient. So we first tried label propagation and self-training based solutions from semi-supervised learning. They are computationally expensive, and therefore we decided to switch to another solution that can be more efficient in our case. And we decided to adopt a CNN-based solution. This is not only the performance issues, but also the false positive rate of autoencoder-based solution, because CNN networks has shift invariant property where the CNN model can detect patterns in different features of the input. So this, we thought that it can be useful, and then we employed this solution. So for the CNN case, probably you mostly know the convolutional neural networks. They are mainly used for image processing. There's a convolution layer where you apply the kernel or set of kernels to extract specific features. We have a pooling layer to reduce the number of parameters to make it easy to manage computations in the further layers. And we have an activation layer. This is used for the controlling the learning process, and also the fully connected layer, obtaining correlation between the previous layer and the next layers. So in our solution, we have the following architecture. We have a full CNN-based model, but we used only the part of this model for the pre-training process, and we processed unlabeled these records for the training of this model. Then after we obtained this model, we used the labeled records in the second step, which is called as V-training. Of course, since this is the adapted solution from another domain, we change the input-output parameters of some layers respectively, as you can see in the table. And initial results show that we have 68% accuracy, which is very close to post solution, and 90% average precision, which is higher than the post solution. So we decided to go further for this study, and we tried to optimize our solution. Please note that we were trying to do it in a fast way, so therefore we did it empirically, but usually it is better to use some optimization technique for hyperparameter optimization, like simulated annealing, or I don't know, maybe swarm optimization. It can be useful, but we directly jump into the problem intuitively, and we set some boundaries for the hyperparameters, and we optimize them. So the resulting solution is really performant when compared to post solution. The accuracy is 88% on the average, as you can see. Of course, there are some cases for that corresponds to 31%, but this is mainly due to we are using random sampling in our solution, because we have 62 labeled data only. We can make a clear cut for the training and the test data. Therefore, we are applying random sampling, and for each training phase, we are starting the training with the new randomly selected data from scratch, and then we are testing the solution based on the new test data, which is also randomly selected. So according to precision, recall, and F1 scores, it is also giving good average values. We repeated our tests for 100 times, and those are the solutions. And on the left-hand side in the figure, you are seeing that the receiving operating characteristics curve for the best detection performance of our solution. As you know, in order to publish it as a scientific research paper, we need to prove that it is also performant on the public data. Therefore, we use SS7 simulator, and we generate a new simulated data set. And we repeated our experiments on those data sets for both post methods and for our solution. As you can see that on the average case and on minimum for all cases, CNN-based approach is really very performant when compared to the Horn scheme, the post solution, I mean. So for the conclusion, we worked on a CNN-based solution for the detection of SS7 attacks. We employ semi-supervised learning approach in our solution because we have a less amount of labeled data when compared to the unlabeled ones. There are also some other studies that use JSS7 attack simulator. So I thought that it would be better to give the results in here in order to make the feeling that how efficient our solution is. So there are, as I said, many different studies. They are using different techniques for the detection, and like rule-based, seasonal, hybrid, extreme, studentized, deviate, algorithm, k-means, pattern recognition, artificial neural network, etc. So according to our results, our solution and post solution are more effective in terms of detecting attacks for the SMS interception attacks mainly. As I said in the beginning, the vulnerabilities in SS7 networks are still valid for diameter case, for 4G case. Diameter is the name of the core network protocol for 4G. So people can also apply the same approach for attacks. So we can extend our study for 4G networks. We are planning to extend our study for other types of attacks that target category 3 messages. And also, we are still trying to find a way to use our solution for the security of 5G core network security for 5G core networks. So this is the end of my presentation.
Thank you so much, Orhan, for your nice talk. So I'm opening the discussion. So whoever wants to ask questions, just switch on your mic and ask question. I have a few. So I can start. Maybe in the slide 11 you showed, I'm not sure if it is my correct understanding, whether my understanding is correct, but you consider to first select some reduced order feature space and then to apply your framework onto that. And my question is
this slide you mean?
Slide 11, yes, you showed that you have 43
yes.
But
for our solution, I think it's 60.
60. Well, okay, so my question is, how do you select these features? Is it a standard, or you use some autoencoders or other
No, no, no.
techniques to represent the...
Those are not standard features, but this is the features that are taken from post attack detection tool mainly. So the cyber defense group of Post, they worked on this problem attack detection in SS7 networks, and based on the characteristics of Luxembourg, so you can go to visiting networks very easily in here, and in terms of the roaming case, they decided to work with 43 features. So they initiated those features, but in our analysis, we saw that some of those features are not effective. So they are 0 or they are 1 for both cases. So we decided that maybe we can reduce this size, and if we reduce this size, then the solution that we will use will be more effective in terms of differentiating attacks from the normal traffic. Then we decided to go for mutual information and mean absolute difference, and take the intersection of those two sets that we obtained from.
I see. But those features were could be obtained from the raw data that you
yes, indeed.
had in your hands.
Yeah, you can think this like that. So I can give you an example for this case. So you are, for instance, I am in the office for the moment. I am in Belvoir. 5 minutes later, I am in Belvoir, for instance. But 5 minutes later, I am in, let's say, Arlo. So this is a problem because when you take my mobility records, I am moving normally. I'm walking or driving a car, but it is not go from here to Arlon in 5 minutes, for instance. So this is the main case. Without extracting those data, they have also some decoding tool that decodes the data from the raw, for decoding the raw data, and they are generating new features out of those data.
But do you have access to the raw data or not?
Yes, no, I don't have an access to the raw data.
So this 11 gigabyte or megabyte, millions of data.
This is already decoded data.
Encoded.
Probably, yeah, because of the GDPR, I think it is not that possible to obtain those information. So even now they are using some anonymization on the data, but with the raw data, I think it's pretty hard to get the raw. Yeah, it is usually like this when you work with the telecom operators, because I was previously working in France and we were working in Orange for some project. So we need some GDPR data for using privacy preserving clustering. The data that they give us are from Africa, I think. It should be France location data, but yeah, usually you can get the whole package. So this is
so the features are the data that is obtained from the real data, but they are anonymized in the way that you get only the features, right? But the telecom company, they can have access to these data.
Yes, indeed they have.
Yeah. So they can use tools, the attack detection tools that operate on the raw data.
Yeah.
Normally, is it true?
Yeah, exactly.
So they have an advantage that they could come up with a solution that is more suitable. It is not based on the manual construction of the features, but they can use some techniques to produce some more suitable feature space.
Yeah. Actually, what they did recently is that they changed the feature set, but I don't know the latest version of it. So we are still discussing the case because the project was for 2 years and we are in the second year, and maybe we can go for the 4G case as well. We are planning to do this. then I will learn the new features, or if we adapt this for the 5G solution, I will learn the new feature set and I will have a chance to work on that. So the only thing I have is that 62 labeled data and 11 million unlabeled data based on those 43 features.
I see. I don't know. May I have another question about this? The input to your convolutional neural network. So what's the input to your network? Say
yeah, those are the features extracted from the original feature set in this case. Yeah,
but how do you? What's the size or what's the structure of the input? Because CNN.
Yeah, I understand your question now. So we are using 1D CNN. The original solution was also 1D CNN. So this is a raw data only. Yeah, 31 inputs. Yeah, with 31 fields. Yeah, raw data.
But is it a time series or what's this? I mean, how it is organized as an input?
Records are time series, but the record itself is not a time series data.
So the input to your CNN is 31 real numbers, right?
Yes, yeah.
And the output is Boolean.
Boolean, yes.
Whether it is an attack or not attack.
But we have only two cases in the data set, whether it is attack or not. We don't. There are no subcategories for the attacks. We have only one type of attack or normal data.
I see.
Maybe if we increase the number of classes, if we consider different attacks with this solution, maybe this will be not that performant. But for two class case, it is yeah, good.
So, and how many labeled cases did you have? The attacking cases.
I don't remember the exact value, but the ratio should be 1 to, yeah. I think there were like 20 to 24 labeled attack data, and the rest were the normal data.
I see.
Something around 20.
Okay.
For the attack case.
Not sure. Are there questions from the audience? Mauro, please go ahead.
Hi. First of all, good morning. Thank you for the presentation. It was very interesting. I'm studying online learning, and this comes to my mind if there is some kind of concept drift during training. Do you know it? If, for example, if you trained your model with data from 1 year ago and you tested it now, it would perform differently?
Maybe I don't know. It depends on. Yeah, for instance, post now, although it is working with 70%, almost 70% accuracy, they have a tool for 2 years. So if you take data from, I don't know, 3 years ago, and if you take data from now, yeah, if you try to train the model by using 3 years ago's data, then I don't know, maybe it can have positive or negative effects. Yeah, they can indeed have some effects on the data. I think. Yeah, exactly. It depends on how much attack data that you process. I think it also changes the behavior of the network. Usually, if, for instance, if the randomly selected set contains more attack data inside of it for the retraining phase, and even if you have less amount of attacks in the test case, it is more performant as far as I can see from the results. So yeah, because of the tool, there will be an effect in the data set. The data set will change, but mainly the idea is not changing. The most problematic part is that
The data set is too
usually,
small. The labels.
yeah, they are applying the same approach for over the years, and it still works. So this is really annoying.
Okay, thanks. So I think that probably the concepts do not change, but if you train with different data, of course, that you may have different.
Yeah, sure. Of course, there are some other attack techniques as well. So yeah, it will also change the results, I think. For instance, we have binary outputs for the classification result, and if we have more attacks that we try to classify, then yeah, probably the accuracy will decrease, in my opinion.
Yeah, harder to detect more different kinds of attacks. Yeah. Okay. Thank you.
Thank you, Mauro. Are there any questions? I have one, let's say, methodological question related to the very use of convolutional neural network. Because normally, as you properly mentioned, that they were developed for image analysis, and they took advantage on some geometrical location of pixels or voxels that you were analyzing. So that this geometrical location and positions was quite crucial to propose this convolutional window that was sliding over the image. And as far as I understood, in your case, your features are organized quite randomly on the vector, right? So there is no particular better or worse choice of arrangement of these features. And my question is whether you were considering a different approach that could take advantage of this non-organized data structure. I mean, because assuming that this particular organization of your data has some meaning, well, it may not always work, or you may fall into a trap when applying CNN to that. And there are some approaches that are based on this attention mechanism, like transformers or perceiver, that maybe could be more useful in that particular application. Have you been considering this, maybe?
Yeah. For my case, I am rather a security person than a machine learning guy. But I'm using machine learning for the research perspective. So the idea that we plan to use this approach for our solution is that, as I said in the beginning, there was another study which is using 1D CNN based solution for traffic classification. So this is also raw data. I'm talking about vectoral data. Actually, it is better to say it like this. This is why we thought that we have the similar type of data and we have less classes in here. Maybe it can be useful for our case. But another idea is that if you use the autoencoder based approach, for some cases it is working. But for some other cases, like if I go back this slide, for some other cases, for instance, the post method detected the normal traffic as an attack because of the short duration between two consecutive update location events. So actually, I didn't go into details, but for this study, we were mostly focusing on some specific type of events that we use for the message exchanges that the telecom core network use actually. So according to post solution, since they reduced the problem into just threshold check problem, it is not that useful. So this is why we thought that this CNN-based approach can be more useful. So for the image case, of course, you are right. It is getting some more information from the different locations as well, but we are doing the same thing in here as well. This is why our solution is more effective. But for the future cases, I don't know, maybe or maybe not. Yeah, it depends on the data set that we are dealing with, actually.
All right, I understand. Thanks for your answer. All right, I cannot see any more questions from the audience. So thank you, Orhan, for your presentation,
Jakub,
for the discussion. Thank you all for appearing today. So I will stop recording.